Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrunner, and today I want to talk about how to understand frequency response plots. So once you have the gain function, you can plot the frequency response. Okay, before we do that, let's look for a moment at this transfer function. Okay, so this transfer function has a s squared in the numerator. That means you're going to have two zeros located at 0. Okay, and then you can take the denominator to determine your poles. So just use the quadratic equation. You'll solve for s, and you will get two complex numbers, and those will be your poles. So here's a pole zero map I obtained from MATLAB. We have two zeros at 0. See, here's the real axis, here's the imaginary axis. And you just have to read the graphs carefully. Okay, so here's two zeros at 0. And then we have two poles, and they are complex, so it's a complex pair of poles. And it's about minus 7.5 plus j 0.7. So minus 0.75 to minus 0.7, estimated. Okay, MATLAB will actually tell you the exact values if you want to know. So that gives us some sense of where the pole zero map is. In this class, we are not going to worry too much about the poles and zeros, although I wanted to bring that up to relate it to your other classes. Okay, you can, from the poles and zeros, using techniques you learn in other classes, estimate the frequency response. However, you can just go to MATLAB and get the actual frequency response. So estimating the frequency response might help give you some insight into what is going on, but really to get the actual frequency response, it's just as easy to go to MATLAB. So let me blow up on that. Okay, so there's a couple things I want to point out. We looked at this before, but I want to really bring it home right now. So along the bottom, we have the frequency, okay, in radians per second, and it goes 10 to the minus 2, 10 to the minus 1, 10 to the 0, 10 to the 1. Okay, so this is a log plot. And also, we have a log on the magnitude here. And as I said last time, the reason we want to do log plots is we're talking about very large differences in numbers. So on the x-axis, we're going from 10 to the minus 2 all the way up to 10 to the 1. On the magnitude, we're going from 10 to the minus 5 up to 10 to the 0. So those are big areas. So if you have not been used to looking at log plots before, you might have some problems reading them. So let me just go ahead and emphasize this, okay? Here's 10 to the minus 2. So that's 1 times 10 to the minus 2, 2 times 10 to the minus 2, 3 times 10 to the minus 2. Look, that's about halfway between them. 4 times 10 to the minus 2, 5 times 10 to the minus 2, 6 times 10 to the minus 2, 7 times 10 to the minus 2, 8 times 10 to the minus 2, 9 times 10 to the minus 2, and then we go to 1 times 10 to the minus 1. Okay, so there's not a step where you get 0. That really freaks people out. Don't let it happen to you on a test. Okay, so 10 to the minus 1 is 0.1, so now I can talk a little bit easier. So here's 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. Okay, 10 to the 0 is 1. Then we'd have, well, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I just wanted to point that out in excruciating detail because that is the most common mistake on problems like this on tests. If I ask you, what is the magnitude of the frequency at 0.1 radians per second, you would go to the 0.1, 10 to the minus 1, go up, and then read looking over. Okay, and then we'd have to figure out where that is. Let me go ahead and put that in with a line. Okay, estimating, because I'm drawing with without a ruler or anything. But if we look at the y-axis, you also see that that is also a log plot. So here we have 10 to the minus 5, 10 to the minus 4, 10 to the minus 3, 10 to the minus 2, 10 to the minus 1, 10 to the 0. Okay, so that means that the y-intercept is between 10 to the minus 5, minus 4, minus 3, 10 to the minus 3, and 10 to the minus 2. Okay, when you're reading log plots, if you go 1, 2, 3, 3 is approximately halfway through. So similarly, when you're reading log plots, if I were right here, where I just drew, that would be about 0.3. So we're not much above that. You can estimate that as, so it would be 10 to the minus 3 times halfway is 0.4. 10 to the minus 3 times 4, not 0.4. Halfway through would be 3. So maybe it's 4. Okay. Certainly you can, if you have this on MATLAB, you can zoom in and get the exact value. But I just want you to be able to be close. I want you to know that that is not halfway. That's not 0.5. Okay. No way it's 0.5. So I want you to be able to read a little bit of these graphs. Say, what is the magnitude at 1 radian per second? 1 radian per second is here. I go up. And usually we can actually, sometimes you have graphs on both sides. We do here. So we go over here. Oops. Let me go ahead and color it in. And you see that we're about halfway through between. So 10 to the minus 5, minus 4, minus 3, minus 2, minus 1. We have 3 times 10 to the minus 1 is pretty much where we are at that point. So now let me do a harder one. Let's do 4 times 10 to the minus 1. So what is the magnitude at 4 times 10 to the minus 1? That's 0.4 radians per second. So I first have to find it. Here's 1, 2, 3, 4. This is where people mess up. 1, 2, 3, 4. Go up. Go over. Oops. Okay. And it looks like it's about minus 3, minus 2, minus 1. Nope, sorry. Minus 5, minus 4, minus 3, minus 2. So it looks like about like maybe 8 times 10 to the minus 2. So that'll give you some sense of what's going on. We have the same way that we read the phase degree. Okay, so again, if I were looking at, say, 0.1 radians per second, I would come up here, go over and read. And now this, if you notice, on this left side, now we do not have a log plot. We have a linear plot. So this is called semilog. Semilog. The previous one was called log-log. Okay, so let's read that. We come here, 0.1 radians per second, go over. It's about halfway in between those two. So halfway between would be 175 degrees. Okay, so you just read that off. I just want you to be really careful to make sure you're reading the graph correctly. Now if we do again the 0.4 radians per second, I come up here, and I can go to the left or the right, doesn't matter. And it looks more like 140 degrees. Okay, so again, you're reading kind of approximately, but you've got to make sure that you start at the right place so you can get the answers. Now, let's look at the frequency response function again. Here we have our frequency response, our transfer function written in terms of S. All we need to do then to find the frequency response is plug in S is equal to j omega. So that would give us j omega squared on the top. And then you plug in j omega for all the s's and simplify, and you end up minus omega squared over 2 minus 2 omega squared plus j times 3 omega. So this is basically a complex number divided by a complex number, right? So, well, I guess in this case, it's a real number divided by a complex number. So we have to be able to manipulate complex numbers. So you could plug this in using Euler's identity and solve for a value, for any particular value of omega. If you want to graph it for omega in general, which is your radian frequency, then you would just leave it in this form. Okay, let's look at another situation. What if I want to ask the question, what is the output for a particular sinusoidal input? Now, most inputs are not going to be sinusoids, but they can be written as a sum of sinusoids. And I think it will help you to understand what's going on to look at it for just one input that's a single sinusoid. So suppose I have some value, Vn of t is equal to 2 times cosine 2t. So what is the amplitude? The amplitude is what's in front of the cosine, so it's going to be 2 volts. The angular frequency, omega, is what's in front of the t, so that's 2 radians per second. And we don't have an angle after the t, right? So we could write this as 2 cosine 2t plus 0. So that 0 is our phase angle, V. Okay? So there's our input. Let's see what the output would be. What we're going to do is, we know that omega was 2 radians per second for our example. Okay, so we plug in omega is equal to 2, and we come up with a value. Okay, we write it in rectangular form, polar form, doesn't matter. So here it is in rectangular form, here it is in polar form, and here it is in the number form. So if you evaluate this right here, you end up with an actual number. But to figure out what the output is going to be, you just need to realize that this is basically what you're going to increase the gain by, the magnitude of the circuit. So we take 2, right? We had an amplitude of 2. Let me go ahead and make a note of that for you. This is your amplitude. So you had 2 times this value here. We had a cosine, so we still have a cosine. This value here was our omega, so we put omega 2t. Our previous phi was phase angle of the input was previously 0, right? For the original. And A was 2, just for your reference. Okay, so what we're going to do is we then add this angle, which is 45 degrees, right? 45 degrees. Multiply it out, and you see that for this particular input that I told you, you have this exact output. This is a fundamental theorem in linear circuit theory. So if you have an input and you have the transfer function, you can multiply them together and figure out the output. In this case, we're just considering a particular value of omega. So we can define the frequency response h of j omega to be the eigenvalue of the linear circuit. That goes back to your math classes. And then the signal e to the j omega t will be an eigenfunction of that same linear circuit. So let's look at this graphically. Suppose our input is Vn of t is equal to 2 cosine 2t. By using our transfer function and substituting in the values for the input, we can calculate the output to be about 0.94 cosine 2t plus 45 degrees. If we look at the graph I have plotted, you can see, again, the input is in blue, and the output is in red, and it makes quite a bit of sense, right? So you see that the input goes from 2 down to -2. The frequency, if you wanted to look at it, you could calculate it. It's about 2 radians per second. It is 2 radians per second. The frequency of the output is also 2 radians per second. But you can see there is a phase change between them, and that is because V out is at an angle of 45 degrees. So here's the MATLAB code to make all those plots in case you wanted to see it. I created B and A, okay, and plotted those. I plotted a pole zero map. I plotted freq S, that was our frequency response. And then you can go through some activity here to actually plot your frequencies, your input and output signals. So for those of you who like to do a little MATLAB, here's an example you can follow. So we've done several things in this group of recordings. We've looked at how to solve for a passive circuit gain. Remember, passive circuits contain resistors, inductors, and capacitors. We can figure out how to determine the circuit's frequency response. We know that if a sinusoid is the input to a particular linear circuit, its magnitude and phase will be altered by the evaluation of the frequency response at that particular sinusoidal frequency. So the frequency response of the circuit determines what the output is going to be. Okay, MATLAB will do these computations for you. Thanks for watching. I hope this helps you to understand frequency response plots.